Let's talk about models, but particularly climate models. What you just saw were some peculiar models in a sense. They were machines that were sort of lifelike. And I wanted you to watch that to give you perhaps an intuitive sense of what a model is. A model is something that's built to simulate something that is real or natural. And climate models are no different. Climate models, instead of being made of pipes and wires and pieces of fabric, are made of equations. They're made of math. But the intent is the same. These equations are intended to simulate our planet's, in the case of climate models, climate. So I want to give you a little sense of how these models are designed and how they're used so that you can be better equipped to understand climate change and make compelling arguments as to its public health importance. As you know, we can measure temperature, so we have temperature data, as you've seen before, going back to the 19th century that's based upon thermometers. But that's not what climate models are used for. Climate models are used to tell us what the temperature and the climate more broadly on Earth will be in the future. And the question that one of the questions that climate models try and answer among many is how much warmer will it get on Earth? The climate has many variables, as are pictured here. So there are variables related to the world's oceans. There are variables related to the land. There are such as how much green is on the surface of the Earth or how much white. White, as you know, reflects heat energy better than black, which absorbs. The point of this slide is not necessarily for you to memorize all of these potential variables that might go into a climate model, but to give you a sense of the sophistication of climate models, that they do consider many, many different variables that are relevant to how the Earth's climate would respond given changes to greenhouse gas concentrations that are increasing because of fossil fuel combustion or deforestation, which also releases greenhouse gases into the atmosphere, or other perturbations to the climate system. Climate models have gotten more sophisticated over time. As you can see here, going back to the 1990s to the present day, the climate models that have been used have gotten increasingly more refined at a spatial scale. So the Earth in climate models is divided into cubes, and those cubes that climate models, the equations that drive climate models operate within, have gotten smaller and smaller over time. So you can see between 1990 and 2007, we've gone from roughly a 500 kilometer squared cube to a 110 kilometer squared cube. At the same time, there are also more levels in climate models. So in the 1990s, there were 19 levels in the atmosphere. Now we're getting closer to 40, as well as more levels in the world's oceans. So there's greater spatial resolution, as it's called in the climate models. And there are more and more components. So this just shows you that over time, climate models have used more and more Earth systems in their mix. So atmosphere has always been a part of it, land and surface area, but now we're talking about land ice and atmosphere chemistry being into these models. In the most recent IPCC report talks about those as well. So climate models use equations. They use them at increasingly more refined spatial scales with more variables. And they measure all factors that relate to warming using what's called radiative forcing. Distance is measured in feet and meters. Eggs are measured by the dozen. Weight is measured in pounds or kilograms. But radiative forcing is measured in watts per meter squared. So it's unit of power per square area. Radiative forcing is a measure of how much a factor alters the balance of incoming and outgoing energy in the Earth atmosphere system. So whether it be greenhouse gases or particulates in the air from volcanoes or clouds or ice, all of these things exert radiative forcing and that is the measure of how much they change this balance of incoming versus outgoing radiation. They're based upon the 1750 baseline, so you have to set a 0 point for radiative forcing because you're essentially saying, does something affect the balance? And you have to set a 0 point, so it's relatively arbitrarily chosen at 1750, which is clearly pre-industrial. They're measured, as we mentioned, in watts per meter squared. And importantly, at equilibrium. So not everything that changes the radiation, the heat balance of the planet happens instantaneously. In fact, most things take time, including greenhouse gases, to equilibrate. Greenhouse gases, many of you may know, are not just in the atmosphere, they get absorbed into the ocean. There's an exchange there. Carbon dioxide also gets absorbed into plants. Over very long time scales, it gets absorbed into rocks. And so when we talk about radiative forcing, it's intended to be the effect that whatever the factor that's under consideration is moving, however it's moving, to be at equilibrium. So once it's been distributed between the various places it's going to go. So the next slide I'm going to show you is a bit messy, but it is important to try and grasp. It's a summary of all the various radiative forcing components that go into climate models. And as you can see at the top are greenhouse gases in the top section. Towards the bottom you see some natural phenomena like clouds and albedo change from land changes to land use. And then also the sun. The most important thing to note here, there are two very important things out here. One are the three red bars at the bottom of this slide. Those are the total anthropogenic, meaning human-driven, radiative forcings relative to 1750. And you can see they've grown over time. And as of 2011, there's a substantial over 2 watt per meter squared change in radiative forcing. And the largest driver of that, as you can see from this slide, is carbon dioxide, the very top brown-colored bar. There are some significant uncertainties here, the biggest of which is cloud adjustments due to aerosols. You'll see the error bars there are quite large. Even with that, the scientific community feels confident that whatever variability may be not well described now in clouds is not substantially changing the net effect of carbon dioxide and other greenhouse gases upon radiative forcing and, as a result, the warming of the planet. So this is a more sophisticated version of a slide that I've shown before. It shows the greenhouse effect, but here it includes the various radiative forcing components like aerosols, clouds, ozone, greenhouse gases, and surface factors. And so it gives you a slightly more nuanced view of how the greenhouse effect works that includes considerations of these various components of radiative forcing. Again, not critical for you to understand every last piece of this, but it's starting to help you form a more clear picture, hopefully, of how scientists understand how our climate changes and the various forces that are driving climate change, be it deforestation, changes to land use, melting of ice, and so forth. Some of you who've been thinking along with me as we've gone through this are probably starting to ask, well, how do we know the climate models are accurate? After all, predicting the future is not an easy exercise, and with so many variables involved, how could we possibly get a reasonable estimate of how the climate will change? Well, there's several ways that climate scientists do that. So, for instance, we know that greenhouse gases have physical properties. We know that ice reflects a certain amount of radiation. We know that ocean currents transport heat in certain ways. And so the models are designed to be based on those physical principles and less so upon the data, because the first thing one might say is, well, of course they're going to accurately predict the past if their models have been strictly based upon how all of that data. But the models are not designed based upon that data. They're based upon the physical principles that drive that data. So with that as background, look at these two graphs here. The top graph shows you a red line, which is model data. There are some 58 simulations produced by 14 models represented in the top red line. The black line are observations, and what you'll see here is a fairly good concordance going back to the start of the 20th century between the models and the data. Now, if you look at the bottom graph, you'll see that the blue line is all of those models, but with the greenhouse gases, the human-driven and the human components of climate change removed. So it's just the so-called natural forcings. And you'll see shortly after World War II that the curves start to diverge, and by the present time there's a large gap, statistically significant gap between those two curves. So there's a couple points here. One, this clearly shows that the models perform better when the greenhouse gases are included than without. But the other crucial point is that there are no other variables, or variable for that matter, that can improve the fit of the climate models to the data than greenhouse gases. So it's not just that the skeptics will argue that the models don't work, because they do, but it's also that there's no better explanation as to what's going on. So it's not as though there's an alternative hypothesis that would explain the inability of these models to work, given the absence of greenhouse gases. So what do these models say about warming going forward? This is a similar figure, except here we're talking about the RCPs in terms of overall emissions of greenhouse gases, and the black dots represent what we've done. And you'll see here that we have largely stayed on the business as usual trajectory up until the present. And so there is time to switch that trajectory, but as you can see, the further along we get, the harder it is to switch course. Models by no means are perfect. Again, these are scenarios, and many things could change. For one, about population growth, about economics, about how much greenhouse gases we put into the atmosphere, our ability to take them out of the atmosphere. There are many things that could change. But I think it's also important that the models themselves are limited. And I'll just mention a few of those. The first is that models are discrete. So you remember we mentioned that the models operate on a spatial scale, and they also operate on a temporal scale. So they march through time at intervals. Nature, of course, is continuous, and what you see here are a pixelation effect on a picture. So 0% pixelation, 5% pixelation, and 20% pixelation. And so you can imagine that if you pixelate a climate model too much, you might not get as clear a picture as you need to about the future, and that's certainly the case. So it's important to be cautious about climate models that have been spatially scaled to a very small local area. And that's important because when we're planning for public health preparedness, it's important to understand that climate models can't necessarily give us accurate or necessarily precision at very small spatial scales at the level of a city, for instance. Not that they're irrelevant, but I think it's important to recognize their limitations in that regard. This is also something to bear in mind. This was a graphic that Mario Molina, a Nobel Prize-winning chemist, he won the Nobel Prize for understanding stratospheric ozone depletion due to chlorofluorocarbons. He used this metaphor in a talk he gave about how climate change is sort of like this puzzle, and climate models are sort of like this puzzle where we sort of know all the pieces and we've started to put them together, and we've begun to see a picture emerge, and we can pretty clearly understand what that picture is, even if all the pieces might not be exactly in the right place or located necessarily right next to where they're supposed to be. And again, this is a nice metaphor, I think, because it aptly describes where we're at with climate modeling. They're not perfect, everything isn't exact, but they're certainly clear enough to make us be able to understand to the extent that we need about where particularly public health interventions may be useful, where we can expect disease burdens to perhaps occur, and to make intelligent choices about what to do, both in terms of mitigation, meaning reducing the amount of greenhouse gases that go into the atmosphere, and also in terms of adaptation or preparedness. So what can we do once climate change is set in?